Hello everyone, Professor Dustin here, and this video is going to be a short introduction to charge, conductors, and insulators. So first, just a few real basic properties about what charge is in physics. So just real basically, objects can have charges just like they can have mass. So just like an object can be a mass of 1 kilogram or 2 kilograms or 3 kilograms, those objects can also have charges. Now, what is a charge? Well, just like a mass is something that interacts gravitationally. A charge is something which interacts electrically. And so they're going to be very analogous, those two concepts. But there is one really important difference between charge and mass, and that is that mass is a gravitational interaction, always attractive. Two objects with positive masses, there can no negative masses allowed in the universe, positive masses attracting each other. Charges can have both positive and negative sign, and therefore they can be either attractive or repulsive. And actually, that's kind of two things, right? So it can be attractive or repulsive because it can have different signs, positive or negative. Where Q is the charge of an object, and I can say that charge can either be positive or it can be negative. So that's a real basic introduction to what charges are. I'm not really saying what they are. I'm kind of saying what the effect is that we see. We see that objects can have charges. Now, there are three basic properties that charge has in physics. So let's do those next. So charge is quantized. So what the word quantized here means, you may know of this thing called quantum mechanics, which is a huge topic in physics. But in this context, quantized just means comes in little itty-bitty packets. So you can't get any charge in the entire world you want. You have to get charges in chunks of electron charge. The electron charge is with a minus sign because the electron is negatively charged, 1.6 times 10 to the minus 19 coulombs. So you can probably tell coulomb is the unit of charge. 1 coulomb is a huge charge, right? 1 electron has 10 to the minus 19 of them. But really the important part for quantization is that you can't get any arbitrary charge that you like. You have to get a multiple of the electron charge, 3, 4, 5 electron charges, a mole of electrons also, right? So in common parlance, we don't actually experience this because we can charge, 1 or 2 electrons is a tiny amount of charge. So it looks to us like it's a continuous amount of charge from 0 up to some amount of charge. But in reality, we're adding individual electrons to that charge, not little chunks of electrons. It looks continuous, but really we're just adding single electrons. The second thing is that the value of the electronic charge is independent of its type. So that's kind of a strange thing to say, but what it means is that the smallest negative charge you can get is that, smallest positive charge you can get is also that, but positive. So it's either that's going to be the smallest positive charge or that's going to be the smallest negative charge. All you can do is get multiples of those two positive or negative charges. And the last thing we have is that charge is conserved. So charge is conserved in the same way that we learned last semester that energy and momentum is conserved. Whatever the initial amount of charges that the system has to be the amount of charges is at the end. Now, just like for energy and momentum, there are conditions on that, right? The system has to be closed. There isn't any other excess charge around that is being added to the system. So in many ways, the conservation of momentum happened if there's no transfer of momentum is conserved. Well, that's kind of two statements that mean the same thing. If you don't transfer any momentum, then clearly the amount of momentum is conserved. Charge is the same. If the system is closed, meaning there's no charges being transferred, then charge is conserved in that system. More specifically, we'll often think about systems as like two balls with charges being transferred in between them, and we'll think about that as like a conservation of charge thing. But conservation of charge is a law of physics in the same way that energy and momentum is conserved is a law of physics. Okay, so let's briefly talk about conductors and insulators. Basically, there's two kinds of objects in the world when it comes to charges. There are objects where charges can move around freely on them. Those are called conductors. And there are objects where charges cannot move freely upon them. Those things are called inductors. Examples of conductors would be like wires in your house, right? Because of those wires transfer electricity around to different parts of your house. Example of an insulator is actually for wires. It's the plastic stuff that's going around the wire that prevents the electricity from flowing to your body when you grab it, right? So those are two examples of conductors and insulators. So I'm going to do a quick demo in the lab to show you some of the interesting things that happen between conductors and insulators. Okay, so I'm going to try some simple experiments to show you the differences between an insulator and a conductor. Remember, a conductor is an object that allows electrons to flow freely through it, whereas an insulator is one that does not allow electrons to flow freely through it. Insulators are like this plastic rod, this wool, right? They do not allow electrons to flow, whereas I have for my conductor this metal ball, which is probably made of brass or something, connected to a little S brass piece down here. And then I have another insulator, which is a sort of cardboard tube down here as well. So the cardboard tube is insulated from the metal part, but the metal part is all one conductor. So just because something's a conductor and an insulator doesn't mean that you can't charge it. So you can add charges to either of those two kinds of objects. It's kind of tricky to do it. You're going to see me try, but you can try to add charges to them, and then on the conductor, those added charges also will flow around, whereas on the insulator, the added charges will not flow around. So the best way to add charges to an insulator is doing something like this. These are both insulators, but the wool, because it's like little fibery, you can like rip electrons off of the wool and add them to the rod just by friction. So I'm going to first try to do that, add electrons to the rod using the, rub the wool and the rod together, basically the way that static electricity works when you like rub your feet on a carpet, right? Do that. And then what I'm going to try to do is show you how charges in the presence of the conductor will move the charges around on the conductor surface without actually touching the conductor. So that's the first thing I'm going to try. This is the part that sometimes doesn't work, is charging up the rod. So if you kind of give it like some of these, like, as if you were, scraping your feet across the surface. Yeah, it's not totally working. I'm going to try it a couple more times. There we go. So you can see that what happened is the rod got charged. I think I've added electrons to the rod. And then when I move the rod close to the conductor, the charges in the conductor are moving around in response to the presence of the charges in the rod. In this case, the charges on the rod are negative, so there's positive charge flowing to that vicinity of the conductor, and there's negative charge flowing down to the bottom of the conductor, and the negative charge that's being added to the conductor is now making the net charge on the insulator has a net charge on it, but it has positive and negative charges. They're pushing those positive and negative charges away from each other. But you can see that charge differential that's happening goes away as soon as I remove this guy. So the charges just move around freely on the conductor, whereas they don't move freely on the insulator. Now, I can transfer the charges from the insulator to the conductor by touching it. So I'm going to do that by doing that. And in principle, I'm trying to get them all off because they're all over the surface. Yeah, so now I've transferred the charges from the insulator to the conductor, and now that insulator down there is feeling lots of charge differences because now there's a net charge on a conductor. It's probably a charge negative because I think those were net electrons, and I think I've added electrons to it. So now I've got a charged conductor just like I had a charged insulator. Now I can remove those charges, and generally you can always remove charges by doing something called grounding. So grounding is basically, there's an infinite source of charge, either positive or negative, in the ground, which is the earth. So just like your home wiring system has that third wire in the plug, that takes it directly to ground. Probably there's like a metal pole somewhere in your house that wire is directly connected to. The easiest way to do that is to find somewhere in the lab that has a direct pipe, because pipes are typically directly coupled to the ground. So this is the old like gas piping into this lab, so I think that's probably a good ground. So what I'm going to do is I'm just going to take this wire, which is connected to the pipe, and touch it to the conductor, and in principle, any excess charge on the conductor will flow to the ground. Great, you see that exactly what happened. All the excess charge that was causing that deflection got sucked off and flowed to the ground. Because on the conductor, it's easy for charge to move. So as soon as there's an opportunity for it to move, like go from it to the ground, it does it immediately. Okay, cool. So real basics of insulators and conductors. So let's talk through just a little bit. I won't do the whole thing, but just real quick, what happened in that lab experiment. So I had the ball. The ball was neutrally charged. Everything in the universe starts neutrally charged. Until you charge it, objects are generally neutrally charged. Because they would, if they were not neutrally charged, they'd start flying over there or doing whatever. So if they're in equilibrium, like sitting in front of you, they're generally neutrally charged. First thing I did was I added charge to the rod. Now, some objects you can add charge as positive charges, some you can add as negative. I'm pretty sure that I added negative charge to that rod, so I'm going to indicate that, and I'm going to do 3. And actually, I should add the lower part of the system as well, just like that weird S thing. Doesn't really matter. It's whatever that weird hooky thing was. So as I put the the insulating rod that's now charged with negative charges close to the conducting sphere, there was a charge separation. Now, like charges repel, unlike charges attract. So the positive charges wanted to hang out here because they were close to the negative charges. The negative charges didn't want to do that because as soon as the positive charges moved, the negative charges went, I don't want to be near you. So they went and I zoomed down here. Now, notice it's still neutral because the total charge is 0. But now there's a charge separation. So let's pause there and let me redraw it. So now I've touched the rod to the conducting ball. So what happens there is that the rod loses its electrons because the conductor can easily move electrons around on it. It's not easy to move electrons off of inductors, but if you have some force between the conductor, the conductor and the insulator, then the charges will get sucked off of it. So what happened was that those 3 charges got sucked on to the conductor. So in reality, just for like a split second, they were like negative, 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 positive, positive, just as they got launched off of the inductor. And then down here, we still had negative. Now, this situation is kind of not a static situation because now we have an inductor which has some net charge on it. So those charges are actually going to rearrange themselves to try to make them as neutral as possible. So it's not totally obvious how those charges are going to rearrange themselves. Let me try to draw one picture which might show you what's going on. So they're going to redistribute themselves in a way so that the conductor is as neutral as possible. Now there's 1, 2, 3, 4, 5 negative charges and 2 positive charges. So there's more negative than positive. The thing is now not neutral. But maybe the negative charges will try to spread themselves out like that, and maybe the positive charges will kind of get in there. Whatever. It tries to rearrange itself so that the whole system is as neutral as possible. Then what I did is I took a cord and grounded this conductor. The sort of notation for that is you usually do something like this. That's usually a sign for ground to indicate that I am now connecting this to ground. Now, all the excess charges flowed into the ground. So what was the excess charge? I have plus 2, minus 3. So there's, minus 5. So there's a minus 3 net charge. So 3 negative charges, negative, 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 flowed to the ground. And so then I can redraw my picture from after the 3 negative charges leave, where now I'm back to 2 and 2 at the original place. So I don't know, again, I don't know how they're arranged. Maybe there's a positive, positive, negative, negative, some even distribution, right? So this is the process by which of what I showed you in the lab. This is a little confusing, but we just need to, this is just a consequence of the fact that some objects are conductors and allow electrons to flow. Some objects are insulators and allow charges and don't allow charges to flow. They did all this experimentally before they understood about the conservation of charge and about the quantization of charge. But this is sort of the background for how we start studying about charges. Okay, great. I hope that has been helpful to try to illustrate what charge is and also what this conductor and insulator thing is all about. Thanks for watching, and I'll see you in class.